Hello everyone, welcome to my channel, The Big Boolean Theory. This video is part of a lecture series on operating systems, and currently we are on the second module of this course, that is process management, right? And within this module, we are trying to understand how does the operating system manage the CPU by providing this abstraction of a process, right? And within the second module, currently we are on the third topic, that is system calls, exceptions, and interrupts, right? So the idea behind this topic is to understand what are the different ways in which the process can communicate. Not only the process, in we want to study in the ways in which the process and the operating system can communicate with each other, right? And the three methods that we are going to study are system calls, exceptions, and interrupts. So basically, these are events that happen during the execution of a process, and they are, as I said, different ways in which the process and the operating system communicate with each other, right? So we are going to start this topic with the concept of system calls, right? And later on, after spending quite a few videos on system calls, on understanding system calls, later on we will shift our focus to exceptions and interrupts in the later part of the topic. So in this video, let's start with the basic like introduction to system calls and understand at a very high level what is a system call. So without further ado, let's get started. So let us try and understand what is a system call through this diagram. So this is a very basic diagram which is giving our current understanding of how we look at the process execution, right? So let me explain this diagram. So there are two parts in this diagram. The first one is the kernel, and the which is shown in red color, and the other part is the user process. So these are two regions, and the user process is shown in blue color. So what do these regions mean? So basically, from left to right, here the time is increasing, right? And here basically we are showing that the process is executing. It is executing instructions, right? So let us see what are all the events that happen during the life of a process, right? The first thing that happens is the process creation, right? The first step is the creation of a process, and this red arrow means that currently we are executing kernel code. So it is the operating system. So the kernel is the core part of the operating system. So it is the operating system which will be creating the process, right? So this first arrow is showing that part of execution where we are executing the kernel code, and the kernel has created the process, and then it will launch the process, and there will be a transfer of control. Okay, so this arrow that is shown in black color with a blue highlight, so this arrow is basically the transfer of control from the kernel code to the user process. Now we are going to start executing the actual instructions of the user process, right? So the main function, the instructions which will be part of the main function inside the user process, those instructions we are going to execute, and this blue line, this blue arrow represents that, right? So the second step was the starting of execution. You can think of it as jumping to the first instruction in the main. Okay, and then this third part is the execution of instructions. These are the actual instructions which are part of the user process, right? And then let's look at the fourth step. So after the last instruction has been executed in the main function, and we are returning from the main function, then the process basically, now we are going to start the termination of the process. So the user process like requests the kernel to initiate the termination. So first of all, there will be a transfer of control from the user process to the kernel, right? So this red arrow, right, this is saying that it is now the end of execution is now initiated. Okay, so once we reach into the kernel again, this part of the execution will happen in kernel code. The kernel will now clean up the process, terminate the process, and release all the resources that were acquired by the process. So this is a basic diagram. There are 5 steps in this diagram. We start the process, transfer the control, execute the instruction, transfer the control back to the kernel, and then terminate the process, right? So both the kernel and the user process instructions are being executed. So this diagram, as I said, kind of depicts our current understanding of how the life cycle of a process looks like. A very simple life cycle. Okay. Now, as you can see, there is a basic assumption here that once the user process has started its execution, the control does not go back into the kernel before the termination, right? Here we do not see any transfers of control back to the kernel during the execution. We see that only when the process has finished, according to this diagram, according to our current understanding, we see that only when the process has finished executing all of its instruction, then only we are going back into the kernel. But the diagram is inaccurate, right? So the actual so a more realistic picture looks something like this. Okay, so what has changed? So if you see now, there are two shifts into the kernel, and then we also return back to the execution. So there are two such transitions, and as you can see, these are labeled as system calls. So what are these system calls? Basically, during the execution of a process, there are several occasions when the user process needs some services from the operating system, and these services or operations can only be performed by the operating system. So the user process during execution makes such requests, and these requests are system calls. So let us see how these requests look like and what are these requests for. So these requests are for operations which only the operating system can do. For example, it could be some operation on some file. So let's say reading a file. Okay, it could be writing a file, opening a file, and so on, right? So the basic idea is that file, the concept of a file, it's an abstraction over the IO devices and the storage, right? We have talked about this in the first topic only, first module only, right? Since this abstraction of a file is created by the operating system, then any operation on this abstraction, that is the file, that has to be performed by the operating system. The user process cannot do it. So the user process requests the operating system to perform one such operation, that is reading a file. Let's look at some other examples. This is the mmap system call. So as you can see, the system calls look just like function calls, right? We'll look at how the system calls look in more detail, but as you can see, they look just like function calls. Okay. So this mmap system call, this is used for allocating memory in the address space, right? So again, we know that the address space is an abstraction that has been created over the memory, right? Since this abstraction was created by the operating system, any operation on any such abstraction has to be performed by the operating system. The user process cannot do it on its own. It does not have control over its own address space. It has to request the operating system to do such operations for the user process. So it is another example, right? So as you can see, during the execution of the process, there are several occasions in which the user process requests such services, and these services come in the form of system calls. Whenever the user process makes a system call, and the system call looks just like a function call, whenever the user process makes such requests, then the control is transferred into the kernel. Some kernel code is executed. Here the kernel will perform the requested operation for the user process, and when that operation has been finished, the results are returned back to the user process, and the user process, as you can see, resumes the execution from the point it had left, right? So some user code was being executed, and then there was a system call. So at that point, the control was transferred to the operating system, and then some kernel code was executed, and then back to the user code. And this happens multiple times during the execution of the process. Here we see there are two system calls, but in reality, there are a lot of system calls that happen during the execution of user process. So the point is that a more accurate picture of the life of a process looks something like this, where the execution alternates between executing kernel code, then user code, then kernel code, then user code, and so on, right? It starts with the kernel, where the kernel is creating the process, then it goes to the user process, the main function starts executing, and then it keeps on alternating, right? The user process executes some instructions, then it makes a system call, the kernel is invoked, and then the kernel returns the results, and so on. The execution proceeds until the final request from the user process to execute to terminate the process. That is also a system call, right? This transition that you see here, the user process is making a request to terminate itself. That again is a system call, right? So this was how the basic execution goes like, and now we have a basic idea that the system call is like a function call which transfers control into the operating system. And what does it do? It performs some operation on behalf of the user process. The user process requests certain services, and it is the system calls, it is inside the system call code where the operating system fulfills those requests, right? So I have a very basic diagram of how you should think about a system call. So let's say this is the user application, and this is the main function, this is the code. So this is the system call. As I said, a system call looks like a function call. And here I have taken a dummy system call which is named as sys underscore call, right? So let's say the sys call is made, and as we know, the sys call is a routine or a function that is defined in the operating system's code, right? This is not like a normal function when we call, the control is transferred to somewhere within the user application. This is a function call which transfers the control into the operating system, and the code for this system call is defined in the operating system's code base. Okay, so when the system call is made, the control will be transferred to the operating system. The operating system will perform the requested operation and then return the results, right? So as you can see, a system call looks just like a function call, but it transfers control into the operating system. And once the results are returned, then the process can resume its execution. So this was the basic idea behind the system calls. So now we are going to look at a very brief demo of strace tool. So what is this tool? The strace tool is a tool in Unix based operating system, which is used to find out the or trace out the system calls which were made when the program was executed. So the S here kind of stands for system call, and we are trying to trace all of the system calls that are being made or that are being invoked when the process is executed via this tool. So let us take a look at this tool. So in order to understand the strace tool, I have a very simple piece of code here for you. It's a simple code written in C, and all it does is that it has one single statement, that is print hello, right? It just prints hello. So let me go ahead and execute this piece of code. So I have already compiled this. The executable is /hello. So let me execute this executable, and as you can see, the hello message was printed onto the screen. So this is a very simple piece of code, right? Now we are going to see what are all the different system calls that were made when this piece of code was executed. Just guess the amount of system calls that would have been there when this piece of code was executed. We'll just now see, right? But do make a guess. So let me use the strace tool. Okay, so the way this tool works is that this is the tool name, this is the tool binary, and here we give one argument, that is which program that we what is the program executable that we want to trace. Here we want to trace the /hello, and then we specify the one file where we want to store the output. So this -o flag is for specifying the output path. So let us go ahead and execute this. So again, the program was executed, and the strace output was in this output.txt. So as you can see here, we have the output.txt. So we have a lot of output on this screen. Let us try to understand what is here on the screen. Okay, so each line here represents a system call. On every line there is a system call and the return value that was returned by the system call. So as you can see, there were 39 system calls made during this simple code where there was just one piece of printf statement. 39 system calls. Okay, or each line represents a system call, and you can see there were so many system calls in this piece of code. So let me try to show you all the system, not all the system calls, a few of the system calls that would make sense to you. Okay, so the most important system call is the write system call, the one that we can straight away understand. Here you can see the write system call is printing the string hello, right? In order to print this hello string to the console, so we are trying to print the hello string to the monitor, right? We're trying to print this to the monitor, which is an IO device, and it is the operating system which will do it. So here, and as we know, all the IO devices are represented as files. So this write system call writes this string into some file, the standard output. The one stands for standard output. This is the file descriptor. Okay, so we'll not go into too much detail, but yeah, we understood this write system call, which is trying to print the hello message to the string, to the console. Then this exit group system call is for process termination, right? After the work has been performed, this exit is used to terminate the process. Let's see some other system calls. This first system call execv is the system call that is used for launching this piece of program. You can see /hello, right? This /hello is the piece of name of the executable that we just executed, and this is the system call that is used for launching the process. Okay, then there are some other system calls. Here you can see there is open system call. There are two open system calls, right? And what they do, they read from some files. And what are they reading? They are reading all the dependencies that are required to run this executable. Okay, so you can see the C library, the libc. This is the libc is being loaded from some file, right? The C runtime is required to execute this piece of code. Okay, What are the other things that we can look at? There are a lot of read here, read system calls. So wait, something, sorry. So this read system call is used to basically read from some files. Okay, so you can see here we had opened the files and now we are reading the files. We are reading some files, and then again here another thing is the mmap. So the mmap system call is used for allocating the memory. So here I'm just making a guess, I'm not really sure, but I'm very like I guess that the four system calls for memory allocations here are for the address space, right? We're trying to create the address space. Okay, the different sections that we saw, the code section, the data section, heap section, the stack section, here the system is trying to create the address space. That is my hunch. Okay, then yeah, then mmap is where we're trying to deallocate the memory. Okay, this brk system call is again used to increase the size of the heap section. So all of these, there you can see there are several system calls. The point is not to understand all of these system calls at this point. I just wanted to make a case that within a very simple piece of code also, like as simple as a single printf statement, you can see a whole bunch of system calls that were made, right? So you see how much the user process relies on the operating system to get its job done, right? It is requesting services from the operating system constantly throughout its execution, right? And that is how it can communicate with the operating system and get its work done. So guys, this was it for this video. In this video, we discussed at a very high level what is a system call. We introduced it at a very high level. You can think of a system call as a function call. You can see all of these look like function calls, right? But the difference between a system call and a normal function call is that a system call transfers control to a routine inside the operating system. And what does that routine do? That routine executes some operation on behalf of the user process. The user process requested the operating system to do something for it, and then the operating system performs the same, right? So this was a brief introduction to a system call, and also we looked at a brief demo of the Strace tool where we saw that there are so many system calls that are made during the life of a process. So guys, that was it for this video. Thank you very much for watching, and I will see you in the next video. Thank you.